There are basically three types of chemical bonds: ionic, covalent, and metallic. We're going to focus on ionic and metallic bonds today. But in order to do that, we have to go back to covalent bonds. Remember, in covalent bonds, electrons are being shared by atoms. In a perfect world, they share equally. All animals are created equal, but some are more equal than others. That's a quote from George Orwell's Animal Farm. Why am I mixing your English class with chemistry? Well, we can easily swap animals for atoms. It turns out these atoms don't all play fair. Let's look at hydrogen atoms that bond with an oxygen atom. These atoms are sharing electrons, which makes this a covalent bond. But here's the thing, oxygen has 8 protons in the nucleus, while each hydrogen only has one pathetic little proton in their nuclei. The ability for oxygen to attract the electrons is stronger than the hydrogen's ability. This is known as electronegativity. But I think of it as electron bullying, because oxygen is going to have the electrons around its nucleus more often than the hydrogens have electrons around theirs. As a result, the oxygen side becomes slightly negative, and the hydrogens become slightly positive. This is an example of a polar covalent bond. The positive and negative ends create poles like the ends of a magnet, and they'll even arrange themselves based on this polarity. These water molecules prefer to have opposite ends near each other. The slightly negative oxygen ends are near the slightly positive hydrogen ends. The lowercase Greek letter delta is used to represent the slight charge. The polarity of water makes it great at dissolving lots of substances that are also polar. But how can you tell which substances will be polar or nonpolar in the first place? Charts are awesome, you guys. This one lists the electronegativities of most of the elements. The higher number means they have a higher affinity for the electrons, and the electrons will spend more time near that element. You don't have to memorize them all if you notice the general trend of increasing electronegativity toward fluorine. But maybe you noticed the noble gases don't have electronegativity values. That's because only a few of them will even react with other elements, and it's under very specific circumstances. Their electronegativities are unknown. When two elements with very similar electronegativities bond, like hydrogen and carbon, they form nonpolar bonds. Electrons are shared fairly equally. When elements like hydrogen and fluorine bond, they form polar covalent bonds, where they are shared unequally. Fluorine gets it more. When elements like francium and fluorine bond, their electronegativities are so extreme that sharing doesn't even happen. It's bullying, and fluorine straight up steals the electrons. But you know how in kindergarten a boy might pick on a girl because he has a crush? Well, after the stealing occurs, the atoms become attracted to one another and form an ionic bond. More like ironic bond. Oh god, I'm sorry. Finally, we're ready to talk about ionic bonds. Let's start with lithium and fluorine. Both of them are unhappy with the number of valence electrons they have, and they also have very different electronegativities. Lithium, a metal, has 1 valence electron. Fluorine, a nonmetal, has 7 valence electrons. If they get near enough to each other, a reaction will occur. Watch closely. Now lithium is positively charged because it lost an electron. Fluorine is negatively charged because it gained the electron. They are attracted, and when they form an ionic bond, those charges cancel, and they become a neutral compound. In truth, you never really have 1 lithium and 1 fluorine reacting. Ionic compounds form crystalline structures with multiple atoms involved. Here's the reality for ionic bonds. If we want to talk about the simplest theoretical bond, it's correct to call it a formula unit. So here's a formula unit of lithium fluoride. It has 1 lithium atom for every 1 fluorine atom. But not all ionic compounds are the same. Remember valence electrons? The easy way to figure them out is to count across the families of the representative elements. Everyone wants to be like the plastics, the noble gases. They have full valence shells. Atoms need to either lose or gain electrons to fill their valence shells, and they usually choose the easiest route. Take lithium. It can either gain 7 electrons to be like neon, or lose 1 to be like helium. Yeah, lose just 1 and become a +1 cation. The alkali metals become +1 cations, alkaline earth metals +2, borons +3. Carbons can go either way with a plus or -4, but they usually don't. They're really good at sharing and typically form covalent bonds. Nitrogens will gain 3 and become a -3 anion, oxygens -2, and halogens -1. At this point, it's like a mix and match game. You just throw in a cation and an anion and watch them fall in love. It's chemistry. You know, like chemistry. Oh god, I'm so sorry, I did it again. Here's a cation, here's an anion. All we have to do is make sure their charges neutralize when they come together. If I have just one of each, we would have leftover positive charge. Luckily, we don't do reactions one atom at a time. We usually dump things together. So we have a ton of fluorines laying around. One more and we have a total of 0, a neutral compound. There's a quick trick to this that I call the drop and switch. Let's use magnesium and aluminum. You can draw each of them out to solve the formula, or drop and switch the superscripts. The formula is Mg3Al2. It works because 3 times 2 is 6 in both cases. Sometimes you'll use polyatomic ions, which are compounds that have covalent bonds and an ionic charge. They behave just like any other ion that you would use. Let's try sodium and the carbonate ion. The drop and switch trick works, just like before. But be careful not to confuse the super and subscripts. Don't actually write a 1 when you drop and switch. Let's try one more. Barium and phosphate. Drop and switch. When you write the formula, use parentheses around the phosphate ion to show that you have 2 of the entire ion. Oh yeah, it's time for the good stuff. Naming ionic compounds is certainly trickier than naming binary covalent molecules, but there are some basic rules that will help you. Say the metal first. How do you know which ones are metals? They are to the left of the metalloids on the periodic table, except hydrogen. If there are multiple metals in the compound, the cation goes first. Add "-ide to the last word in the name, just like naming covalent compounds. Third, polyatomic ions have special names. Just say them as they are. Either look them up or memorize them. Odds are you're going to memorize some whether you like it or not, based on how often you use them. Transition metals need Roman numerals that match their ionic charge when you write the name out, but not for the formula. Old school people will say the classical name, like cupric chloride. Not all of the elements have cool Latin names though, so the stock name is best. Let's do a little practice. How would you name this? It's sodium chloride. Metal first and then "-ide" at the end. Li2S is lithium sulfide. Notice there are no prefixes. You only use those in covalent bonds. KOH. Here we have a polyatomic ion that likes to hide. This is potassium hydroxide. If you can't find it on the periodic table, it's probably on the polyatomic ions list. FeCl2. Iron is a transition metal. We have to deduce its charge from the anion. You can think of this as a reverse drop and switch. This is iron 2 chloride because the 2 chlorine atoms provide a -2 charge, and the whole compound must be neutral. N2O5. Now I'm messing with you. Nitrogen and oxygen are both nonmetals, which means this is a covalent bond and the formula must have prefixes. Dinitrogen pentoxide it is. This looks covalent at first, but it's actually made of 2 polyatomic ions. It's ammonium carbonate. The last type of bond, metallic bonds, are lesser known, but still awesome. Imagine these are the atoms of aluminum. Each aluminum atom has 3 valence electrons. Metals are smart. They realize they can remain stable if they let their valence electrons roam freely. They create a sea of electrons. This is also what allows metals to conduct electricity, since electricity is the flow of electrons. Metals are also malleable and ductile. These magnetic buckyballs are representing the atoms of an element, like aluminum. Metals can be hammered into thin sheets, which means they are malleable. They can also be drawn into thin wires, which is ductility. Let's compare and contrast some of the properties of the 3 types of chemical bonds. Ionic bonds occur between a metal and a nonmetal, covalent between 2 nonmetals, and metallic between 2 metals. Ionic bonds involve the transfer of electrons, covalent share electrons, and metallic have a sea of electrons. Ionic compounds will conduct electricity when they're aqueous or molten, and that's because the bond will break, forming ions, which are electrolytes. Covalent compounds don't conduct electricity well or at all, and metallic substances conduct electricity as solids. Both ionic and covalent compounds are brittle, while metallic ones are malleable and ductile. Ionic compounds have relatively high melting and boiling points. Covalent compounds are relatively low, and metallic ranges from low to high. Ionic bonds occur between atoms with extreme differences in their electronegativity. Covalent bonds both have high electronegativity, with slight variations, and metallic bonds have low electronegativity. Ionic compounds exist as a crystal lattice. Covalent compounds are molecules, and metallic bonds form compact, orderly crystalline patterns. Ionic compounds don't use prefixes in the naming, covalent compounds do, and we don't have a naming convention for metal alloys. Ionic compounds are generally soluble in water, covalent compounds will vary, and metallic compounds are insoluble or reactive in water. Ionic compounds are solid at room temperature, covalent can be solid or liquid at room temperature, and metallic compounds are solid, with one exception, at room temperature. Happy studying!